Welcome everybody to today's Combustion webinar. Today we have as our speaker Gus Nathan from the University of Adelaide in South Australia. Gus needs really no introduction, but for those of you not familiar with his work, he's focused on combustion and the transition to low carbon fuels, and is going to tell us today about some of the work that he's been doing for the transformation of high temperature process heat into zero or net zero CO2 emissions, and some of the technologies and science behind that. So with that, I will turn it straight over to Gus. Before we start, we'd like anybody who has questions to just put them into the chat box at the bottom of the window, and I'll collect them and ask them one at a time at the end of the lecture. So the floor is yours, Nathan. Gus.
Thank you, Isaac, and thank you all for the opportunity to talk, and I very much look forward to the opportunity for the discussion. We in our centre have increasingly been moving towards looking at the high temperature process heat and the opportunities to assist in the transformation to net zero emissions. Well, I'll try to give a bit of an overview as to the drivers and the reasons and where this transition is up to give you more of an idea about some of those opportunities, and then also to some of the research that we're doing in this area as well. I'd like to acknowledge that I'm part of a big team at Adelaide, and so there are many other contributors, some of whose work will be contributed here. So I guess in background, the high temperature process heat sector is typically used to produce some of the energy intensive products that are vital to the global economy, such as cement, steel, aluminium, including mining. There, of course, are many others, copper and the like, although the energy component in the high temperature processing is a smaller component of the net CO2 in many of the other products. But the sector is now beginning to transition to net zero by 2050, and there is a growing number of companies and governments that are committed to this. And obviously this represents a lot of significant challenges. Some of the technology, obviously there's a lot of technology development needed because there is currently no commercially viable pathways that are economic under today's economics, although they're beginning to be implemented quite demonstrated rapidly because these drivers are emerging. So some of the key, I say combustion related, because these are the type of technologies that employ similar related physics to of what we do, and the temperature ranges, although some of them may not be directly combustion in process. These include electrification of the process heat, the production and use of hydrogen, high temperature concentrated solar thermal, and alternative fuels. I guess the alternative fuels have been looked at for quite a bit of time in this community, but some of the others have not been quite so much. And within this, we think there's also hybrids between these systems, not just one, but switching between them, because the variable price of electricity will, for example, vary, and so they'll be desirable to switch between them. Within this, a lot of these, significant number of these high temperature processes involve suspended flows of particles, and again, this has got a lot of the related physics to what has been studied for many years in pulverized fuel combustion, for example. And also some of these processes will be CO2 capture and reuse. And again, there's thermal chemical conversion of the reuse process to other fuels and other chemicals. So a bit about some of the global drivers. This is a recent report from the International Energy Agency showing the global share of the different the different key sectors, global CO2 over the next 50 odd years. And the electricity sector is broadly anticipated to decarbonise first. Then the transport sector, which is the orange, will decarbonise next, and the industry processes are anticipated to be the slowest to decarbonise for a whole host of reasons, including the fact that they're often very capital intensive, trade exposed, but also there aren't clear commercial technologies available on the horizon, well, demonstrated yet. And in this illustrates that this is the 32% here that corresponds to the industrial sector. And of that, about 3/4 of the demand is for heat. of which about half is high temperature and half medium to low temperature. So the high temperature, there are a number of other studies, all of which are showing, this is a different study produced in Science, showing some of the key sectors that have been attributed as being difficult to abate. And these include things like iron and steel and cement, as well as other things that are widely looked at, such as aviation fuels and the like. Cement here is shown as being 4%, but if you include the lime as an industrial chemical, this is often buried in many of these other processes. Overall, some studies put it as between 7% or so, and iron and steel as much as 7 or 8%, depending on which studies that you look at. But these are some of the reasons why they're considered to be difficult to abate, is because the technology is currently unproven, low margins, they're high cost plant with long life, so slow to change, as well as being trade exposed industries. The cost of the change is also quite large in terms of the cost of that commodity in its own right. But despite that, the cost of the change compared to the final product is anticipated to be relatively small, and this is fundamentally the driver. So this is illustrated in this figure, which comes from a recent report, which I think is shown here, though I can't see my part of my screen is blocked. Yeah, there, the Mission Possible source. And so this is illustrated, for example, with steel, that the current price of, you'd expect the price increase to be something like 50% of the current cost of steel to make steel to carbon neutral, which obviously is a big increase from the steel itself. But that 50%, nevertheless, translates to only 1% more in the cost of the final product of something like an automobile. So that 1%, of course, the 50% increase is likely to come down as technology evolves, and the 1% is something that more or less customers are prepared to pay that difference. Likewise, with cement, you see that some estimates have been there might even be 100% or so increase in the cost of cement if it was to be made carbon neutral. In fact, as I say, those costs are also coming down, but that still corresponds to only something like 3% more in the price of a building. So this is why fundamentally now with the global will to change, there's more and more countries and companies signing up to be committed to carbon neutral of 2050. And fundamentally, this is expected that if the customer is prepared to pay this 1%, this will pull back down the market to generate this additional driver for these energy intensive components. So this is fundamentally why industry is starting to invest in this, which obviously, and government, which is also why it's also a growing research opportunity. So this is why some of the studies, such as this Mission Possible study recently, is estimating that there'll be something like a $7 trillion investment in this heavy industry sector, which will be in the transition to net zero. And obviously this will be driving the new technology development, which is very relevant to the kind of research which many of us in the combustion community have been doing for many years, albeit with some differences. So some of the examples of what is illustrating these changes coming through, the top right-hand figure is an illustration of there are already some certified low carbon, not yet carbon zero, but low carbon. This is an aluminium product made by Norsk Hydro in this case, although there are a few other companies also manufacturing it. This 4 tons of carbon per ton of aluminium is about a quarter of the world average of 16. And there are many reasons for that, but mainly historical, because many of these particular aluminium smelters happen to be built close to hydroelectric plants, which allows them to be renewable in that electricity component of these products. But that's a relatively small part of the market. But these are the kind of things that are showing that these low carbon products are emerging. There's also a whole lot of announcements. Groups like Apple and also not shown on this one, but Microsoft, they've all committed to be have net carbon neutral products by 2030, for example. So this is the kind of thing that is driving the investment. So these industrial processes are very bespoke. They tend to be large processes. Many of them, for example, the cement kiln on the top left is about 100 megawatt of a single flame burner. But many processes are very large. These are showing some of the technologies, both current and emerging, for the low carbon products that are emerging. I'll say something about this reactor here a bit later on. But the key characteristics is that each of these systems currently are typically one-off designs, because each process is a little bit unique, because each ore is a little bit different and each got different local conditions. So this is the kind of technology that is also well suited to the need for high technology and kind of good research. You see they're currently provided, the energy is provided by flames, typically with radiation as the dominant mode of heat transfer. And this is one of the challenges of, for example, switching to something like hydrogen, which is a much lower radiation medium, and also some of the electrical heating technologies are not very well suited to this at the moment. So there needs to be quite a bit of development before direct electrification could occur in these kind of processes. And of course, new processes may be developed in the longer term, but in the immediate phase of the transition, the lowest risk is going to be by converting current plants to operate. So we think we need to have alternative energy systems into these kind of reactors. This is the direction that industry is going, and it may be through low carbon fuels such as hydrogen, or it may be these other mix of energy sources. So this is leading to the question that people raise of which pathway do we think it will be? Will it be hydrogen, renewable electricity, CO2 capture and reuse, biomass and waste, or solar thermal? Or maybe it'll be a mix of these different processes. And our view is that it probably will be a mix of these systems. Probably biomass and waste will play a niche role. Obviously, waste is already playing a role in things like cement, but there are limited amounts of that resource, and they probably will have other competing requirements. So we think it's probably going to be a mix of these other systems that will play the biggest contribution into these heavy industrial sectors. So one of the key things about these processes is that in addition to the need for heat, there's also a need for the chemical for the reductant process. And obviously, as engineers, we're aware that iron oxide is an oxide, and the reduction reaction requires a chemical which in a conventional blast furnace is provided by carbon monoxide, which obviously then converts to CO2 in reducing the oxide from the ore. So the reduction by hydrogen has been demonstrated in the lab, and the process is very well known. And also some industrial processes already use something like 2/3 hydrogen made by, for example, reforming of natural gas. So hydrogen is already a significant component, but it hasn't been demonstrated with a nearly pure hydrogen product yet, although these kind of demonstrations are now, at commercial scale, these demonstrations are now on their way. But also in the iron process, of course, steels are typically carbon steels, so some carbon monoxide is likely to be needed, although in the longer term, this is probably going to come from something like a regenerated CO2 rather than from fossil sources if we want to make our products net zero. So this is an example of some of the different processes. The commercial process that's used dominating the industry today is the blast furnace, together with the basic oxygen furnace, and this typically burns coal, which is converted to coke, and the iron ore is firstly pelletized through a sinter type process. So there are different pellet kilns as part of the process, And so this is, of course, leading to the CO2, which is a dominant component. But these blast furnaces have typically got a life of, once they're relined, of more than 20 years. So this means there's a long history. So obviously we want one option is to try and produce the pellets carbon neutral as part of that step. But one of the other processes, this is the one I referred to, this is direct reduced iron with an electric arc furnace. And this is also uses the pellet process, but then it goes into some kind of furnace. It may be a shaft furnace typically. And this furnace, this kind of process, currently there are already commercial processes using natural gas, which generates about, as I say, about 2/3 hydrogen anyway, in terms of the fuel that goes into the reduction furnace. So this process is not too far from being commercially converted to being able to operate with pure hydrogen, and industry is well on the way towards that particular pathway. But there are many other opportunities in this process, including how we're going to get the cost of hydrogen down, and other opportunities in this way. So this is the process, the direct reduced iron furnace, which potentially could be produced with low carbon hydrogen, potentially from renewable electricity, or maybe through some other route, such as natural gas pyrolysis, for example. And so these processes this process with syngas is already commercial and is on the pathway to operating with predominantly hydrogen, as mentioned. So there are various studies saying what we think the break-even, or what is expected to be the break-even price for hydrogen when it would start to compete with coke. And it's typically expected that somewhere around US $2 a kilo is where it would start to make sense commercially without any additional subsidy. So this is driving the trajectory to try and develop technologies for the low carbon. Well, this is one of the pathways for one of the drivers for low carbon hydrogen, and why the $2 target is widely put forwards. Of course, the various hydrogen technologies are, as with all technologies, are on a learning curve to lower cost, and so there are various people predicting that the $2 per kilo is on its way with the commercial systems. However, there are also other technologies being developed to try and bring those costs down, and even the cost is not the only indicator, because it's not just the cost of production, but these processes run continuously. So the cost of storage and delivering sustainable constant flow of hydrogen is also part of what the challenge is going to need to be. So exactly how that is going to happen is still one of the challenges that is being developed. So just recapping the main points I've been trying to make thus far in the presentation. Firstly, the heavy industry sector is vital to the global, national and global economies. For Australia, it's twice as big as our energy exports and triple the value of agriculture and livestock, but it's important around the world for all of our commodities. The cost of decarbonising is significant, but it's affordable because when it's incorporated into the cost of a final product, it only adds a few percent, and this is what is typically driving this transition. And while we think that the market pull and policy is more than enough to overcome this relatively small cost in the final product, even though it's a very big cost for the individual component in the supply chain. This will also cause a lot of changes in the global supply chains. It'll change where some of the low carbon processes are being done. But I won't talk about that too much in this seminar, but we can talk about it in the discussion time if people are interested. But I guess the key point is that from the research perspective is that we think substantial investment in technology is needed to transition these technologies, and there's also the technologies are quite bespoke, and so there's a lot of highly skilled understanding that's going to be needed, and opportunities to lower the cost and bring more cost competitive technologies into this mix, including in the cost reduction of the hydrogen, which is important in iron making, but also obviously could contribute to many of these industrial processes as a process heat. So at our university, we have quite a lot of activities into some of the low carbon hydrogen production systems, including photocatalysis. Greg Meether is the driver of that one. I don't work on it myself, although we could be working on some hybrid options down the track. But some of the ones that I'm also involved in, we have a vortex reactor, which can be used for collecting solar thermal energy with particle systems, but also potentially can be adapted as a low carbon reactor. Methane pyrolysis, I'm going to say a bit about work with bubbling media, molten media, and also we do quite a bit of work on solar gasification, although I won't talk much about that in today's talk. So one of the drivers for the people are interested in around the world, increasingly, there's a growing interest in the pyrolysis of natural gas. So obviously in these typical processes, gasification is well understood. However, biomass is a limited resource, and it's typically thought that there are many competing opportunities to use biomass, and it's probably not going to play a major role in hydrogen, although it has other benefits. Steam methane reforming is obviously the commercial route to hydrogen, but it comes with a CO2 penalty, and also is still quite a significant amount of energy is needed to produce it. Then, on the other hand, the pyrolysis of natural gas is directly cracking the CH4 into solid carbon and hydrogen. So this requires much less enthalpy, only about a third of the enthalpy that is needed for the steam methane reforming. So only about 10% of the net energy content of the fuel is needed to do this production process. So this is some of the chemistry is also quite relevant to some of the soot pH combustion research. It's also aligned with in that side of what we've been involved in the past. And on the other hand, the technology is fairly. There are different levels of technology. There are some elements of natural gas which are with pyrolysis which are actually near commercial. There's some of it is recently being demonstrated using the plasma type technology, but there are quite a range of technologies under development with various opportunities, and potentially if the energy required to drive this reaction can be net zero in carbon, then the net reaction of CO2 could be zero if the carbon has a use and doesn't end up going to CO2. So obviously there are many needs for carbon in society, for things like carbon black through the tyres, but also carbon fibres. Maybe some of those carbon fibres may end up displacing some of the steel industry in the longer term, so that market could grow. Nevertheless, currently the anticipation is that making a valuable product has that has a limited market compared to the size of the hydrogen market. So this is one of the constraints, but nevertheless, it is an opportunity for making some relatively low-cost hydrogen, because the carbon potentially can be more valuable than the hydrogen itself. So this is one of the key drivers for this type of technology. The other point is that because the enthalpy, this temperature of this reaction is typically, depending on the conditions, between 750 and 1200 C, depending on the catalyst, etc. And this temperature is compatible with some of the emerging high temperature concentrating solar thermal technologies. And also because only about 10% of the net energy of the fuel is required, then this potentially is one of the renewable forms of heat that could drive this endothermic reaction here, because it's relatively small and the temperature is potentially compatible with this solar thermal. So some of the technologies under development include a falling particle curtain technology. Sandia National Lab is working on that. Then there's an international collaboration of which we're also contributing in Adelaide, looking at this particle system. This is basically a curtain of particles falling through the focal point of a solar tower, which then heats the particles to high temperatures, and the particles become a storage media. So traditionally, this stored heat has been conceived as going into some kind of turbine for power generation. But of course, the energy can potentially be used directly in some thermochemical plants, which would increase the efficiency of the solar thermal energy by a factor of about 3. And of course, historically, heat has been much cheaper than electricity because electricity is being made from heat. However, maybe we're moving into a world where, at least for parts of the temporal cycle, the equation can be turned around, because maybe electricity may be cheaper than heat. And so this is some of the drivers for potentially using solar thermal in these kind of processes. So let's try to move this in here. So some of the potential opportunities and challenges for combining these two technologies together is that if the solar thermal energy was used to drive this methane pyrolysis, this would eliminate direct CO2 emissions. If the carbon has a useful product, then this would also displace the fossil fuels for things like potentially like plastics and tyres. Then the low cost of potentially this can generate low cost hydrogen, at least to some scale, because of the co-production of a valuable carbon-based product, and also a relatively low cost route to renewable heat, because the, CST is potentially a relatively low cost form of stored heat. And the scale and temperatures are relatively compatible. So nevertheless, these technologies at the high temperature technologies above about 600 degrees are also pre-commercial. And so, so this means that there is also technology development to enable this to occur. But there's also growing interest in bubbling molten metal media as a catalytic reactor. Some of the opportunities of using a bubbling molten metal as the reaction media are that the bubbling generates high rates of heat and mass transport in the reaction path, and the molten metals are both highly reactive and have catalytic properties. And unlike the solid catalysts, if carbon is generated on a solid catalyst, it will tend to coke the catalyst. But if it's generated in a molten bath, then this tends to float to the top. And so therefore the material the surface of the catalyst doesn't get deactivated, and hence it becomes continuously replenished, the surface at least. On the other hand, there are challenges, including safe containment of a hot molten metal, and also the thermal management, how the energy is going to be converted into this reactive media. And also there is really very limited data on this, because obviously it's not very easy to perform measurements inside a molten metal bath. So the work that's been done to date is typically involving reactions at temperatures of above about 1,000 degrees. So one of the things that we've been working on is to try and take the temperature to below the 1,000 degree temperature, which will reduce the containment challenges, because it means that the reactor can be contained within a more conventional metallic materials, albeit potentially with some lining, but it's much safer. But also it's more compatible with the solar thermal temperature. So these are some of the reactors in our laboratory that we've been developing. We're working with a large number of collaborators in this area, and of course there's a number of people who are quite a number of people around the world who are now working on this topic and have been doing for some time. Our work spans some of the reactor development, some of the storage, chemical looping, etc. But I guess probably our main focus is overall on the reactor side. We're also beginning to look at developing some of the laser diagnostic methods that have been applied into soot into some of these pyrolysis environments. We haven't yet performed any measurements in that media, but that is the direction we're moving toward. So one of the examples of some of the work that we have performed is demonstrating gasification of graphite in a molten metal. So this shows that much as a gasification reaction can occur under other conditions in other reacting environment, the temperature is relatively modest at about 900 degrees, which is lower than some of the reactor environments because of the high reactivity of the metal. So nevertheless, we don't think obviously graphite was chosen to avoid some of the challenges of things like biomass and waste, which can also have other complex components, but we were interested in the principle here. But we don't think that, we think there's probably a number of limitations to this process because of the availability of carbon sources. So we're more focused on some of the other media, but showing that the reaction can cycle through this molten metal media stably. But we have been doing work also on molten metal as a solar receiver heat transfer media, and again showing very high rates of heat and mass transport in these kind of systems. So that's the principles are well known, but most work has been done with of course on bubbling reactors with different media other than metals. So one of the systems that we've been working on is a circulating reactor. This is somewhat analogous. Some of you may be working with chemical looping reactors typically done with solid media, where typically a metal is switched between two oxidative states. This is one that's done in a liquid media. We've demonstrated it here in water, as you'll see from this system. But effectively, there are two reactors. In this case, they're not reactors; they're inert because it's in liquid. But at higher temperature, you would have two reaction media, or maybe a molten metal at two oxidative states, and then the media from one goes from the top of one reactor to the bottom of the other and back again. And this is pneumatically circulated, which is not such an issue with an ambient system in water. But at high temperature, there are a limited number of the pumps typically only operate up to modest temperature at molten metals. And so for a high temperature reactor, an aerodynamic circulation has got a lot of potential practical advantages in a reactor. So you'll see here, there's two bubbling systems and some dye is placed into one. And you see the dye circulates back around to this one, up, and then down again the other side. We've been doing, that's just a visual illustration, but we've been working on understanding the dynamics of these systems to assist in the engineering tools and eventually in the design. This particular configuration is not such a practical device, but it's demonstrating the principle of pneumatic circulation. And so we're also working on more practical devices that I won't have time to talk about today. So this just illustrates some of the dimensionless parameters that can be used to characterize the circulation of the fluid through these media, and then there are of course a wide range of different reaction pathways that can be pursued, including this type of methane pyrolysis work that I mentioned. So briefly, this is just a snapshot of the work, but the key points to make on the hydrogen production side is obviously there are many drivers around the world to seek to lower the cost, even though the cost of green hydrogen is going to come down to some extent. by the upscaling of commercial type electrolysis production. Nevertheless, there are other drivers for other systems as well, which will also, particularly to look at continuous supply and accelerate large scale for industrial type processes. So there are a suite of thermochemical pathways that could potentially contribute to these systems, including the pyrolysis and gasification and reforming. People are also looking at things like solar reforming, and so there are also the hybrid processes, including high temperature electrolysis. So there are many thermal opportunities for contributing to potential new pathways into hydrogen production. Then on the molten metal catalysis itself, this is also an emerging field with applications beyond, of course, hydrogen production. And we mentioned some of the potential advantages of avoiding degradation of the catalyst and the high rates of mixing. But there are also challenges, and they need to be better understood for better measurements in them, etc., before these can become commercial as a reactor. So the methane pyrolysis is one of the opportunities because of potential for valuable co-products, and also maybe the solar thermal could provide one of the routes for making this technology carbon neutral, at least in the production of the carbon side of the cycle. So moving beyond the carbon part of the cycle, in the industrial processes, another component is the CO2 capture and reuse, and this is also illustrated by this other diagram of some of the basic chemistry. Limestone is a calcium carbonate, and the conversion of limestone to calcium oxide, which is the core component of concrete, but also this is lime, which is also used as an industrial chemical. Then this doesn't need a reductant, but this heat drives this chemical reaction, which directly drives out CO2 from the limestone itself. Of course, there are other carbonate ores that also may release CO2, including magnesium carbonates, etc. But the biggest one commercially used is the limestone process. So because limestone, or at least lime, is considered to have a long-term demand, although there are, of course, notwithstanding, there are a number of concrete substitutes under development, but still there is expected to be some ongoing demand for lime as a chemical, also because lime is used in production of the alumina process. It's used in pulp and paper making. It's an industrial chemical that's quite widely used. So therefore, for those processes, we need to find a way to manage the CO2, and typically the route that's perceived as being the most commercially viable is the capture and reuse. So again, there's a number of technologies being looked at around the world. This is a cement kiln. In fact, this is commercially it's a two-stage process, but simply shown here as a single reactor for the purposes of illustration. The current process burns fuel and air together, and the calcium carbonate is so that's meant to say CaO. There's a typo there, but then the CO2 from that process then comes out, was mixed with the nitrogen from the combustion, which obviously requires a similar process. Well, requires some way of management. There are of course many technologies being looked at for CO2 capture, but the estimates being done of simply applying commercial routes would lead to something like €80 a tonne to capture this without some further developments. So there are further developments needed before this becomes economic, and the CO2 though that comes out could either be put forward to sequestration or looking at a reuse option. However, the sequestration route is not being seen as being particularly attractive, largely because in many cases it might have to go through the transport, might need to go through residential areas, etc. So broadly, the industry seems to be mostly interested in the reuse option. Of course, to make the product completely carbon neutral, you need to have some other offsets, but these can be looked at through things like mineral carbonation, which we can talk about in the discussion if people are interested. But more broadly, one of the other options is to go for an indirect cement process, whereby simply the heat is added rather than direct combustion. It could be indirect combustion with CO2 management, or a carbon neutral fuel such as hydrogen, or maybe an alternative heat source such as hydrogen, but at least there's no direct combustion products mixed in, so the CO2 is inherently captured. So this could then be potentially reacted with hydrogen and heat to produce products such as methanol, which, whilst not, as I say, completely carbon neutral, are lower carbon than the commercial products, the conventional products from fossil fuels. And then there needs to be some further offset to make the system completely carbon neutral. But this is considered by industry that we're engaged with as being the most attractive path within the system towards net zero. So one of the reactors that we are working with a collaborator is a company called Calix, and this is a indirect reactor where the limestone or other material for cement is passed through a tubular reactor that is then heated from the outside, and then the CO2 is the only gaseous product from this process. So one of the programs that we've been working with this technology, with this company, is to better understand the dynamics of this calcination process in this reactor. And so I'll tell you, in this case, a bit of the work we've been doing on the optical methods to enable direct measurements in this reactor, in situ measurements of particle size and distribution. So actually recently, I can't show you all the results in this because it's premature, but it will be published. And so eventually, but this gives you an idea of the size of this reactor operating at about 1,000 degrees. And some of the methods that we've been developing have recently been published in a different system, which is a backlighted optical method using pulsed LEDs. And effectively, a backlight is put on one side of the particle system that you want to measure, and then on the other side, a long-distance microscopic lens. And Ziwei Sun from our team has done most of the driving of this this technique development. And here we're showing it being demonstrated on a falling curtain of particles, and this is also related to the work on the solar concentrator that I mentioned earlier. Using in this case, the particles are carbo particles of about 150 micron in diameter. So this curtain is a two-dimensional slot, in this case of about 2 millimeters thick, although we're also now applying it in significantly thicker curtains. And as the light passes through this system, there's sufficient, even though there's a lot of attenuation. In fact, in some cases, the opacity of this system is higher than 90%, in this case, and even significantly higher than that. And so as the light passes through, the key factor of optical component, which is used to give discrimination in the line of sight, is by using a long-distance microscopic lens. It has a very, very narrow depth of field. So this means particles that are slightly in front or behind the focal plane will become blurred, and hence by doing some gradient processing of the image, you can remove the particles that are not in the focal plane, and this allows discrimination of the discrimination of what's not in the optical focal plane, which gives you the spatial resolution that's needed. So this is an example. This is the gradient detection method. You see the raw image has got all these particles, many of which are out of focus, and only a few that are in focus. And so these, once you do the gradient detection, everything except these ones that are in the focal plane disappear. And this allows spatial resolution even in very densely laden particle flows. And so this is what we've been using to also do measurements. And this also illustrates The depth of field is depending on the constants you use in the algorithm, it shows that the focal particles can be eliminated into up to plus or minus 0.3 millimeters. So the net spatial resolution in that dimension is about 0.3 millimeters. So we actually recently, so this gives showing that the first time through that curtain, we were able to measure a velocity gradient in the curtain, which hadn't been done before because of the very high dense loading of those particles, which makes other measurement methods difficult. Then we also did some measurements in that reactor, but I won't go into those in detail. One of the other measurement methods we've been developing to assist with measurements in these particle flow reactors is a method to give optically distinct detection of both a tracer phase and a particle phase. So here we did it for research using a polymer. PNNA is a polymer particle which is spherical, and the BAM tracer, which is typically used for phosphothermometry, and so these two methods together, they can be driven at the same wavelength but emit at different time scales and also different wavelengths, which allows them to be discriminated optically. So this work has also recently been submitted for publication, and so this is an example of the kind of methods that are kind of needed to give better understanding of these new reactors, which will be needed for part of this low carbon transition. So obviously we're also doing other work in particle-based flows, including the detection of gas phase temperature and particle phase temperature, but this work has been published previously, so I'm not going to talk about it much now unless some of you are interested. We're also doing work on an alumina process in a program with a number of partners, including Alcoa and Hatch and the government lab CSIRO and University of New South Wales. I'm not going to talk about that in this work, but it's another example of how the reactors themselves, the way in which they're operated, will need to change if we're going to make cost-effective carbon neutral processing. But we can maybe pick up some of these in the discussion time if people are interested. So the final comments before I throw this brief brief presentation over for discussion is that we consider the low carbon transition for industry by 2050 is well and truly underway. It's driven by the global commitments, investor demand, and new markets, but it is a long transition. It's not going to happen overnight because of the large bespoke nature of the industry and because of the need for new technology. So the new technology is needed because commercially viable technologies for net products are still in their infancy. You can't buy green steel on the market. You can't buy carbon neutral aluminium, although you can buy low carbon aluminium, for example. So there's obviously a lot of need for cost reduction, increased reliability and optimization, bearing in mind particularly that each process is tailored for the particular ore. So there's a good need for reliable modeling tools, predictive capability, and cost reduction. And so these are very similar tools to what are widely used in combustion processes, even though the applications may be slightly different in these other types of high temperature processes. But also in terms of the heating source, there's a range of new technologies being developed, including thermal plasmas, radiators, etc., for electrification, alternative fuels, the hydrogen, the biomass waste streams, etc. Solar thermal may play a role in the direct use, as well as CO2 capture and reuse. And of course, the reuse of CO2 also brings in thermochemical pathways. So here I've just given a brief taste of some of the research challenges, but we're certainly happy to discuss them, and hopefully it'll generate some new ideas for potential collaborations. We're certainly interested, but it may also spark some ideas amongst the community and hopefully that might be the case. So I'm going to stop the presentation and look forward to some discussion. Thank you.
Thanks for the introduction and the seminar. It's been really quite interesting and an eye-opener. There's a whole lot more to combustion science than just the science, of course. We do have some questions from the audience, so I'll just go through them one at a time here. The first is from Todd Fonsler. Fonsler, I hope I'm pronouncing that correctly. How carbon intensive is the production of critical materials for battery electric vehicles, such as cobalt, lithium, neodymium, etc.?
Very good question. I'm not a specialist on all of those particular processes. I will make the point that typically, so we run the high temp forum and assess quite a few materials through an expert panel process forum, and what we found is that the more rare the kind of materials are, typically the dominant part of the carbon footprint of those processes comes from the early stage part of the processing, from the mining, from the mineral processing, because they tend to be quite low concentrations. There's a huge amount of energy going into separating these very, very low concentration ores into the final product. So the high temperature component tends to be a relatively small part of the total footprint of these materials. So they're all quite, to some extent, whatever their life cycle emission is, in terms of how much the high temperature step becomes a component of. Really, the main drivers in the high temperature step is in the processes like iron, steel, cement, lime, alumina, and aluminium. It's still significant in other processes such as copper and the like, but it tends to be a relatively smaller bit. And once the main economic driver will be on these other ones first, and once you know how to do it with them, then it'll transition through to these very many other processes which also have a high temperature component in them typically.
Okay, great. Hope that answers the question from Todd. Next one's from myself, actually. It's one question I have is, outside of water versus carbon dioxide, how do the emissions of hydrogen direct iron vary from those from, say, a conventional blast furnace operation? What sort of new emissions might we have to consider in these?
So simply switching from the blast furnace to a DRI process will typically, even running on natural gas, will typically lower the CO2 footprint by something like nearly a half. However, the main the step going to make it hydrogen dominant is not necessarily lowering the net energy, but it will be, obviously, if you can avoid the carbon process and you can make if you were able to make the hydrogen net zero in carbon through green energy or through some other route, that's where the rest of the green steel element comes from replacing the carbon with an alternative reductant.
Okay, just to be a bit more specific in the question, I'm wondering are there any other chemicals that will be produced that we maybe don't want? Aside from reducing CO2, are we going to produce something else that's maybe bad for health, bad for the environment? Are there other chemical processes that hydrogen might induce as opposed to eliminate?
Right. I mean, I think the main component is really how the hydrogen is produced. In terms of the iron making process itself, the DRI route is a somewhat more efficient process, but the main I mean the hydrogen itself doesn't have a significant component in terms of other pollutants in that process, but it's more in how the hydrogen is going to be produced itself is my experience. But I'm not a metallurgist, so there may be other elements that I'm missing. But from the discussions I've had, there's not really any major impacts on the actual process, except of course you need some CO in the material. But in terms of other trace elements, etc., not aware of them.
Yeah, okay. Next question is, how difficult is it to extract process heat from particle-based concentrating solar thermal systems versus, say, conventional methods?
This is a really good question. So, so concentrating solar thermal, the collection of the heat in particles is one part of the equation. Then the question is how that heat is going to be transferred to another media. So for example, the power-based systems, there are various heat exchangers under development. There are some definitely there are some challenges in that because it's not straightforward in transferring the heat to a heat transfer medium. So that's certainly it's certainly an area of need of more research to fully understand it. I think it's a bit of a challenge for some thermochemical processes. The particles may be able to be directly fed into a reactor. If that's the case, it's relatively straightforward. One of the pathways that we've been looking at is to put particles directly into something like a fluidized bed for something like a gasification route. That's one of the reasons. So putting it as basically heat the fluidized bed media in your solar receiver and put that fluidized bed media through the bed. If you can do that, it's relatively straightforward, but still challenging. On the other hand, the question of how you integrate solar thermal heat into a process, into an industrial plant, is actually a very significant challenge. We've looked at that in something like an alumina plant, and it's really quite challenging, we think, to do in that case. I'm not sure the viability is still to be determined, but it's all I can say at the moment is at best it's challenging. I think the place to start would be in certain processes such as lime making is probably one of the most compatible because it's not too big. So it's definitely far from being a foregone conclusion that it would be a good fit. It may fit in some processes, but probably by finding the right reactors, it could make sense. But there's definitely a lot of development needed before that integration pathway can be seen to be clear and viable.
Okay, great. That answers it quite in depth. Next question is, one of the challenges you've touched on a little bit in your talk is that a challenge to cost-effective sector coupling is the co-location of CO2 sources and sinks. For example, where you produce cement might not be the same place that you're producing hydrocarbon fuels, for example. So is there an effective way or a cost-effective way to transport the CO2 from the source production to the site where it's needed?
This is a really good question as well. I think there's no single answer to that, and it's definitely a very active research question, is to find paths that are most viable. Our current perspective is that something like methanol is probably a very good commodity for these kind of reasons. So, for example, I'm sure that many of you will have been on a boiler of some type, like a gas boiler, and you typically find if you go to a gas boiler or a coal boiler, there's probably a bunker of oil somewhere on the site, so that if something goes wrong with the dominant fuel source, they'll switch to the oil to run the plant in that intermittent phase to keep it running. So methanol is the potential alternative fuel that can be stored relatively easy. It's a liquid that's relatively safe. It's not toxic, much easier than something like ammonia, for example. And also it's a commodity that, as a liquid, is easy to transport. So it could also be an alternative feedstock as a commodity that could go into things like plastics. So we think it's a kind of a potential commodity that's probably relatively easy to store, relatively easy to transport, and may fit that mix as being attractive. But it's definitely that's just based on experience and anticipation at the moment. We haven't yet done the proper technical economics. These are the kind of things that there's a lot of work needed to be done to really identify what the most effective pathways are, and I'm sure there's going to be a range of bespoke solutions that will depend on the context.
We had one last final question from Igwang. You mentioned that the catalysts in methane pyrolysis for hydrogen and carbon production, what are the typical catalysts? Why not using gas phase pyrolysis directly, for example?
Yeah. So the moment the metal that we're looking at is, I forgot to mention it in the talk, sorry, but is tin, is the one that's been studied most widely, and there's quite a few groups working on that. Tin has been proven to be stable at these temperatures and to work quite well. There's also quite a few groups who are looking at whether they can find ones that would operate even more effectively. But the operating temperature currently is over 1,000 degrees. And so there's the key challenge is to try and find ways to lower it below that. But tin is the one that we are working with and has probably received the most interest as being confirmed to be a useful catalyst in this process. And that's the one that's probably the one that's had the most attention to date. But there are definitely a lot of groups looking at, can they find ones that are not too expensive, that are more effective at lowering the temperature?
Okay, great. So that is the final question for today. We've run out of time now. So if everybody just turn on their cameras for a moment and thank the speaker, and we'll tie off today's webinar here. Great.